In earlier sections, we investigated the limit as x approaches a certain target point. In this segment, we want to talk about the limit as x approaches infinity or negative infinity. Now, you know, with polynomial functions, the graphs of polynomial functions exit the coordinate plane left and right either infinitely high or infinitely low. That is, they go without bound up or down. And those are, you might say, well, the limit is infinity. Well, no, that's not true. We're looking for a real numbered value that the graph is approaching as x approaches infinity, either left or right. Okay, now this often happens when we have rational functions. Remember, the graphs of rational functions often have horizontal asymptotes. That's going to be an important idea in this notion of limits at infinity. Here's a function. Notice it's a rational function. Here is its graph. We can investigate the notion of limit at infinity by looking at the graph or using a table of values, and we'll talk about some algebraic techniques as well. It should be obvious here that if this is a horizontal asymptote, then the graph is going to snuggle up against that asymptote as x becomes infinitely large. So that graph just gets closer and closer and closer as we go out to the right, closer and closer and closer as we go out to the left. So it should make some sense that the limit then as x approaches infinity for this function will be 3, you see, on our graph. And using a table of values, it's pretty easy to see that it's 3 as well. Because if we take x, now this top row would be x values, and here are f of x values on the bottom row. And I'm starting in the middle. Now think about beginning in the middle and just approaching negative infinity like this. Just take actual values to the left of 0, -1, -10, -100. So as x is approaching negative infinity, you see, what is f of x approaching? Well, here are the f of x's. We have 1.5, 2.97, 2.999, you see 7. So we're getting really close to 3 here, and so we say that the limit as x approaches negative infinity is actually 3. And on the other side, the same way. As x approaches infinity, f of x is approaching what? That's what we're examining here with this table. Turns out that it approaches 3. The notation is as we would expect it to be. The limit as x approaches negative infinity of f of x is 3. The limit as x approaches infinity of f of x is also 3. Now, notice the role that the horizontal asymptote is playing in this. It actually is the position for our limit situation when we're talking about rational functions. And with rational functions, a lot of times that horizontal asymptote is really easy to see. Well, let's take a more formal view of this, and let's talk about a formal definition for a limit at infinity. You know, you remember with limits earlier, generally with limits as at a target point, we were talking about an epsilon delta kind of definition. And let's take a graphical approach to the idea of an epsilon and maybe not a delta, but some other kind of idea. You know, we're talking about given an epsilon greater than 0, and that's just a distance around some target point. And let's say that here is that, I'm going to write that epsilon distance. Here is that epsilon distance around this target point at 3. So I've got this distance. So I'm talking about a distance from that target point. Now, given that epsilon distance, I can give you an m such that whenever x is to the right of m, you see, whenever x is over in this neighborhood, f of x minus this target number L, or the L minus the f of x, the positive value of one of those two, the absolute value of f of x minus L, you see, is smaller than this epsilon distance, or we are within that epsilon region as long as our x is beyond m. Okay, that's the whole idea. And I'm probably making it sound a lot more complicated than it really is. It runs like this. It says, let L be a real number. Now, L is our target value, or our limit idea. The limit as x approaches infinity of f of x is L means that for each epsilon greater than 0, for every distance you see greater than 0, there exists an m greater than 0 such that, and here's this f of x minus L, the absolute value of that, it just means that the relative difference of this taken to be positive, you see, the relative difference of these is within that epsilon region whenever x is greater than m. And the situation works in a similar way to the left. Only to the left, and let's look at it on the graph, it's the same idea. We select an epsilon. It can be infinitely close to the L value, and here is the L, incidentally. So given that epsilon idea, here is my, it's not an M this time, let's call it an N. And so given an epsilon, then I can give you an N such that when x is to the left of N, for these x's, f of x minus L, or L minus f of x, whichever one gives a positive value, or more generally the absolute value of their difference, you see, will be less than this epsilon amount. Or we have that distance assured if we choose x's in that region. All right, it runs like this. The limit as x approaches negative infinity of f of x as L means that for each epsilon greater than 0, there exists an n less than 0, you see, to the left of 0, such that f of x minus L is less than epsilon. That distance between them, you see, is within that epsilon region whenever x is less than n. All right, so that's the formal idea. Now, we're going to make some calculations algebraically here. There is a certain theorem involving limits that we need to look at that will help us with the algebraic technique. It works like this, and it's real easy to understand. The limit as x approaches either positive or negative infinity for this fraction is 0. Now, here are the conditions within the fraction. Now, this x is approaching infinity. It can have a rational exponent on it. Doesn't matter what the rational exponent is. Okay, it's a rational numbered exponent on x, and c is any real number for the numerator. But if this value approaches either positive or negative infinity, this fraction is approaching 0. You see, because what's happening here, I mean, think about this as just 1 for the moment. As x approaches infinity or negative infinity, let's say infinity for discussion purposes, as x gets big, as x gets really, really big, any fixed number over a really, really big number is getting smaller, and the fraction itself is getting smaller and smaller and smaller as x gets bigger and bigger and bigger. So this value, this fraction, is approaching 0. Okay, and we can use that idea in a situation like this. The limit as x approaches infinity of this expression, and we can perform manipulations in this kind of limit at infinity as we did earlier. That is, the limit of this difference is the difference of the limits. That is, it's the limit of this minus the limit of that. We can think of it like that. The limit of a constant is the constant. The limit of this fraction, it fits the model, you see, of that idea. As x gets really, really big, then 7 over the x squared will go to nothingness. So this is 4 minus 0, or 4. Now generally you will not have to go, you won't go through all of this gyration. You'll just look at this and you'll say, well, in this expression, as x gets real big, this fraction will go to 0, and so we say that simply this is 4. So that's the way you'll probably approach it from a manipulative perspective. All right, let me show you a technique that is useful in this algebraic arena, another technique. The limit as x approaches infinity of this fraction. Now, look at the numerator and denominator. You'll notice that if this x gets really, really large and that x gets really, really large, the numerator actually is approaching infinity, the denominator is actually approaching infinity, and infinity over infinity is an indeterminate form. We cannot determine the limit in that form. So what we're going to have to do is change the form of this fraction. We're going to have to manipulate the fraction a little bit to create a situation where, and here's the target on this, you're trying to find a situation where the denominator is in a form where the limit of the denominator is some real number. That's what you're trying to do. And the technique that we're going to use here is to divide out this x, is to get a cancellation opportunity with this x. And to do that, we'll multiply through by 1 over x over 1 over x, a form of 1. Now 1 over x times the 2x is 2x over x. 1 over x times minus 1 is minus 1 over x. 1 over x times 3x, 3x over x. 1 over x times 2 is 2 over x. And then the x's cancel here, 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 here. So we have 2 minus 1 over x, 3 plus 2 over x in the denominator. And now, oh happy day, we're in that nice condition that we're after, because we can think of the limit as x approaches infinity. Now for this constant, now we can apply the limit idea to each of the terms that we see here. We could actually write that down, but generally you won't do that. You probably will not write it down. You'll just consider each item in the fraction as a sort of a separate event. The limit for 2 is 2. The limit of 1 over x, as x goes to infinity, that fraction goes to 0. And the limit for the constant 3 is 3, and the limit for this fraction as x gets really big becomes 0 as well. So we have this, and therefore 2/3. So the limit as x approaches infinity for the original fraction turns out to be 2/3. Let's look at the limit of several more rational functions. Here we have the limit of this rational function. And I want you to notice here that we have an x squared in the denominator and we have an x in the numerator. Now, what we're going to do is divide through by x squared. So we're dividing here by x squared, we're dividing this term by x squared, this term by x squared, this term by x squared, this term by x squared. And arithmetically, algebraically, I should say, this is how it flows. I'm going to show you another way to look at this in just a minute, but these x squares go out, and in this denominator we have 3. That's a key issue here. And then in the numerator we have x over x squared, so we have 2 over x, and here we have 5 over x squared. Now, as x approaches infinity, this fraction goes to 0, this fraction goes to 0, this constant goes to 3, and this fraction goes to 0. So we have 0 over 3, or 0. Now recall that when you constructed the graph of rational functions, you often looked for horizontal asymptotes, and you decided on where that horizontal asymptote would occur by looking at the degree of the numerator compared to the degree of the denominator. That is, the degree of the numerator polynomial compared to the degree of the denominator polynomial. And here we have the degree of the numerator polynomial is smaller than the degree of the denominator polynomial. And when we have a 1 degree difference with the larger degree in the denominator, if you recall, you decided that the horizontal asymptote was the x-axis, and therefore y equals 0, and so that's why we have a 0 here. So we are approaching 0 as x approaches infinity. Now, just imagine that horizontal asymptote as the x-axis. Here's another situation. There were 3 situations. I'm going to show you all 3. And we're going to look at it algebraically, and we're going to think about it graphically. But the limit as x approaches infinity of this one, and I'm going through and I'm dividing by x squared to clear this x squared. So I divide here by x squared, there by x squared, here and here, all by x squared. So I have these x squares go out, and I have 2. This remains as a fraction. These x squares go out, and I have 3. And this remains as a fraction. As x approaches infinity, these 2 fractions go to 0. So I have just 2/3. Now recall from your study of rational functions, when you were graphing, you decided that if the numerator and denominator polynomials were of the same degree, and that's what we have here, then all we need to do is look at their coefficients and make a fraction out of their coefficients, and it turns out that that's the horizontal asymptote. Well, that's the limit here. You see that the limit is the 2/3 here. And the other situation was a situation where the degree of the polynomial in the numerator was greater than the degree of the polynomial in the denominator. And in that circumstance, the asymptote was a slant asymptote. And we had techniques to find that slant asymptote, but it was a slant asymptote at any rate. And think about what happens when a graph approaches a slant asymptote. You see, then the graph will increase or decrease without bound as we approach infinity at either direction. Now, here's how it manifests itself in the algebraic world. We're dividing through by x squared. So every term is divided by x squared, and I'm showing that here. X squared cancels with 2 of the x's up here, and we have 2x in the numerator. And here we leave this fraction alone. Here the x squares go out and we have 3, and here we leave this as a fraction. Now as x approaches infinity, this goes to 0, that goes to 0, this goes to 3, but that rascal goes to infinity. So we have infinity over 3, which means that the limit does not exist. Now if it was 3 over infinity, that would be a different thing. 3 over infinity is 0, you see, but infinity over 3 does not exist, we say. Okay, those are the circumstances in rational functions. You're just analyzing the situation much the same way that you analyzed for horizontal asymptotes when you were in pre-calculus. All right, here's a situation involving a radical, and there are 3 techniques that three special things that I want to show you in this one problem. I'll point them out as I get to them. All right, first of all, we have the limit of this expression. And now we'd like to create a situation where something disappears as x approaches infinity. I mean, after all, as x approaches infinity of this, we can't tell what's going on. And incidentally, we're approaching negative infinity here, so we just can't determine what happens. It kind of looks like from this that the situation goes without bound. That is, it goes to negative infinity. As x gets really big negatively, 3 times a really big negative number gets really big negatively, and so it doesn't look like anything spectacular is going to happen. Well, what we can do when radicals are involved is that we can eliminate, or we can place terms into a fraction. We can create a denominator here by rationalizing the numerator of the implied fraction this over 1. Now I'm rationalizing the numerator, so I'm multiplying by this same binomial with a different sign. So it's 3 minus the square root of 9x squared minus x over the same thing. And parenthesis in here will help us see the multiplication. So in the numerator, it's the sum and difference of binomials. So it's 3x, I should have an x in here, I'm sorry. So it's 3x times 3x, that's 9x squared. And then plus times minus is minus. You know the middle term is going out. And for the last term, it's this times that. Well, it's this squared. And when you square the square root, the radical disappears, so we have the radicand. So it's minus the radicand from above. Now in the denominator, we have 1 times that, or simply that. I just brought it down here. All right, now let's clean up a little bit. 9x squared minus 9x squared. Oh, those go out, so minus x is plus x. So here's what we have. Now, this technique of multiplying by the conjugate is number 1. That's the first item that I wanted to show you. All right, the next item is coming up. We want to divide through now by x. We want to clear this x. So we divide this by x, we divide that by x. Now, but in dividing this by x, we don't accomplish very much. We don't get too far with that. We would like to divide by a form of x that will get us into that radical. Now, how do we get into that radical? Well, it turns out that x is fundamentally equal to the square root of x squared, isn't it? Well, it is in most cases. Now, here's what I said. I said that x is equal to the square root of x squared. Well, that's true as long as x is positive. You see, now here, this is the second technique, this idea of thinking of x as being the square root of x squared when radicals are involved. That's a technique. Now, the third technique is the idea that x is a negative number. But the square root of x squared, a negative number squared is going to be positive. The square root of a positive number is going to be positive. This side is going to be positive. X is going to remain negative. So to maintain the idea that x is approaching negative infinity, to maintain that idea, then x is the same thing, has the same value as the negative of the square root of x squared. You see, so we'll use this as the replacement for x. You see, it's a very creative way of getting ourselves into this radical. So in place of the x, I'm dividing through by x, but the x here we're using as the negative of the square root of x squared. And this is the third of those 3 techniques that I was telling you that I wanted to show you. Now, the minus minus here becomes plus. The radical in both numerator and denominator means we have the square root of the fraction 9x squared minus x over x squared, and that's what we deal with up over here. These x's cancel, those x's cancel, so we have this. 1 over 3. Now, this, it's one radical and numerator denominator. This x squared divides both parts, so we have a cancellation here, and then to give us 9, and then x over x squared is 1 over x. Now we can make some progress when we think about approaching negative infinity, and I forgot my negative signs here. So negative infinity. So as we approach negative infinity, this becomes real big. I don't care if it's negative or positive. It's real big negatively, real big positively. It doesn't matter. This goes to 0. So we have 1 over 3 plus the square root of 9. 3 plus 3 then is 6. So 1/6 then is the limit of that as x approaches negative infinity. So you might want to review this particular problem a couple of times to target those 3 ideas that I was trying to show you. Here's a situation involving trig functions. It's the limit as x approaches infinity of x minus cosine x all over x. And we can divide through by the x and get this. See, the x divides each of these, so it's x over x, or 1, minus cosine x over x. And I'm thinking of it like this. Now, you might, I mean, very quickly we could say, well, gee, the limit of 1 is 1, and the limit as x approaches infinity, we have this x is getting arbitrarily large, and the cosine of any number, regardless of how big, is going to be a number between 0 and 1. So no big deal. So we can say then that this is going to 0. So we have 1 minus 0, or 1. Now, I'd kind of like to show you a rather special way of showing that the limit of this fraction is actually 0. And it turns out that we can use a technique that we studied much earlier called the squeeze theorem. You see, it turns out that we know that cosine x, the cosine of a number, is a number that is between 1 and negative 1. So we could say that negative 1 is less than or equal to cosine x, and cosine x is less than or equal to 1. Now we can think, well, let's divide through by x. So this is this. You see, I'm just creating a situation which we have at cosine x over x situation. And now think about applying limit to this idea. Now I could write limit as x approaches infinity, limit as x approaches infinity, limit as x approaches infinity. But what are we approaching here? This approaches 0. This approaches 0. So if these two approach 0, what's the limit of that? Oh, it's got to be 0. You see, and this is a nice little use of the squeeze theorem here to show that idea.